Good day everyone. Today we are going to tackle about polyprotic acids. Polyprotic acids are unique acids that have the ability to donate more than one proton to a solution. This category includes diprotic acids, which can donate two protons, and triprotic acids capable of donating three. So, polyprotic acids donate multiple protons in water, unlike monoprotic acids. Diprotic acids donate 2, while triprotic acids donate 3. In equilibrium stages, sequential ionization stages with distinct dissociation constant or Ka. Examples of polyprotic acids. Diprotic acids. Common examples include sulfuric acid and carbonic acid, or H2CO3, with sulfuric acid being a strong acid in its first dissociation and weak in the second. Triprotic acids. The best examples include phosphoric acid and arsenic acid, or H3ASO4. Demonstrate multiple dissociation steps with varying strength. Characteristics of polyprotic acids. Polyprotic acids do not release all protons simultaneously. Each ionization has a corresponding dissociation. In the buffering ability, they can effectively resist pH changes due to multiple ionizable protons, and in complex equilibria, multiple dissociation steps create a series of equilibria affecting species concentration and overall acidity. Applications of polyprotic acids. In industrial applications, sulfuric acid is essential for making fertilizers and explosives. In biological functions, carbonic acid helps regulate blood pH levels. In analytical chemistry, used in titration process to identify ionic species. Their behavior. Polyprotic acids can donate multiple protons, leading to various pH levels. In conjugate base strength, the strength conjugate bases diminishes with each deprotonation steps. In chemical process, understanding polyprotic acid is vital neutralization in pH management. Significance in nature and industry. Polyprotic acids are vital in both nature and industry due to their ability to donate multiple protons. A deeper understanding of their behavior can enhance our approaches to chemical reactions. The study of polyprotic acid contributes to applied sciences, environmental studies, and biological science. To help you understand better about our topic, here's a short
There are
video.
also polyprotic acids, or acids that can transfer more than one proton. So let's examine these as well.
An example of this is carbonic acid, or H2CO3. This is a diprotic acid, meaning that it contains two acidic protons. It can deprotonate twice in succession, first giving the bicarbonate anion, and then again to give the carbonate anion. Each of these deprotonations has its own associated Ka value, as the first proton is much more acidic than the second. Ka1 is 4.3 times 10 to the negative 7, while Ka2 is 5.6 times 10 to the negative 11. Some acids can even be triprotic, meaning they can deprotonate 3 times. Phosphoric acid, or H3PO4, is such an acid. Here are the 3 relevant equilibria and their associated Ka values. As we can see, the first proton is much more acidic than the second, by 5 orders of magnitude, and the second is another 5 orders of magnitude more acidic than the third. All of this complicates things like pH calculations quite a bit, as we can't simply take a Ka value and do a simple calculation. Phosphoric acid will produce a certain amount of hydronium by virtue of its first deprotonation, but it will then generate more hydronium upon its second and third deprotonations. And for certain acids, we must consider all of the relevant equilibria in determining the hydronium concentration in solution. However, in the case of a 5 molar solution of phosphoric acid, it is the case that the second and third deprotonations are negligible. We would set up the icebox for the first equilibrium, plug in 5 as the initial concentration and zeros elsewhere, and then assign the relevant change and equilibrium values. We could again make the simplifying assumption to the denominator, do some arithmetic, and we get 0.19 molar as the hydronium concentration. This gives us a pH of 0.72. Then we understand that the solution is also 0.19 molar in H2PO4-, since that is the other product of the first deprotonation, and given that the Ka2 is on the order of 10 to the negative 8, we can see immediately that not enough hydronium will be generated to make a difference in terms of the pH. Sulfuric acid is an example of a diprotic acid that is a strong acid for its first deprotonation to produce the bisulfate ion, but a weak acid for its second deprotonation to produce the sulfate ion, with a Ka of 0.012. And again, for most solutions, the second deprotonation will be negligible when compared with the first for any relevant calculations.